Welcome to a deep dive into the safety architecture of the AEON-CASIMIR vacuum-metric propulsion system. In this chapter, we'll explore how this advanced technology is engineered to remain survivable, predictable, and recoverable, even under the most extreme operating conditions. Unlike conventional aerospace safety models that focus on mechanical failures, AEON-CASIMIR's approach is field-centric, addressing the breakdown of coherence, curvature control, vacuum boundary integrity, and energy phase stability. Here, failure isn't a sudden event, it's a gradual loss of constraint. That's why safety must operate continuously across multiple physical layers, ensuring the system's resilience at every moment. The purpose of Chapter 16 is to formalize the strategies and mechanisms that keep the AEON-CASIMIR system safe and operational, even when faced with the unexpected. The chapter emphasizes that safety isn't just about preventing failures, but about ensuring that any loss of constraint is detected early and managed effectively. By focusing on field-based analysis, the system is able to address complex breakdowns that go beyond simple mechanical issues. This sets the stage for a new paradigm in aerospace safety, one that is proactive, layered, and deeply integrated into the system's core architecture. In AEON-CASIMIR's philosophy, failure is not a single catastrophic event. Instead, it's seen as a gradual process, a slow loss of constraint across different physical domains. This perspective changes everything about how safety is designed. Rather than waiting for something to break, the system is always monitoring, always adapting, and always ready to respond. This continuous vigilance is what allows the system to remain robust and recoverable, even as conditions change rapidly or unexpectedly. AEON-CASIMIR classifies failure modes not by individual components, but by the physical domains in which they occur. This field-based taxonomy allows for a more nuanced understanding of how and why failures happen. By categorizing failures according to electromagnetic instability, plasma containment degradation, Casimir boundary failure, metric control loss, and coupled cascade failures, the system can tailor its responses to the specific nature of each threat. This approach ensures that every type of instability is addressed at its root cause. The first class of failure, electromagnetic instability, involves issues like phase drift between plasma rings, electromagnetic field saturation, loss of harmonic lock, and magnetic reconnection events. The key risk here is rapid decoherence, where the system loses its coordinated behavior without necessarily causing structural damage. By identifying and managing these instabilities early, the system can prevent them from escalating into more serious problems. Class 2 failures are all about plasma containment. These include exceeding the beta limit, plasma wall coupling, density runaway, and toroidal shear collapse. The main risk here is the emergence of localized thermal spikes and the loss of lift symmetry, which can compromise the craft's stability. By monitoring these parameters, the system can intervene before these issues lead to more widespread instability. Class 3 failures focus on the Casimir boundary, where issues like plate spacing, deviation, vacuum pressure inversion, zero-point fluctuation amplification, and negative energy asymmetry can occur. The primary risk is metric instability, which can lead to unintended spacetime curvature. Detecting these subtle changes early is crucial for maintaining the integrity of the propulsion system. Metric control loss is a critical failure mode where tensor misalignment, curvature overshoot, time rate differential instability, and navigation frame desynchronization can occur. The key risk here is causal dislocation or inertial shock, which could have severe consequences for both the craft and its occupants. The system's ability to detect and correct these issues in real time is essential for safe operation. The most complex failure mode is the coupled cascade, where failures propagate across multiple domains. This can involve changes in spacetime geometry, energy states, and plasma dynamics, leading to runaway feedback across all layers. The key risk is that a small issue in one domain can quickly escalate, affecting the entire system. Robust monitoring and containment strategies are vital to prevent these cascades from becoming catastrophic. AEON-CASIMIR's containment philosophy is built on the concept of nested safety shells. Instead of relying on heavy mechanical bulkheads, the system uses redundant field envelopes to protect against failure. This layered approach ensures that if one layer is compromised, the others can take over, maintaining overall system integrity. It's a dynamic, flexible strategy that adapts to changing conditions in real time. The first and most fundamental layer of containment is the primary metric envelope. This layer defines the craft's space-time geometry, providing the foundation for all other safety mechanisms. By controlling the very fabric of space-time around the craft, this envelope ensures that the system remains stable and predictable, even as external conditions fluctuate. The secondary layer is electromagnetic containment. This layer stabilizes both the plasma and the vacuum, acting as a buffer that absorbs and dissipates energy fluctuations. By maintaining electromagnetic stability, this layer helps prevent the kinds of instabilities that can lead to more serious failures in the system. The tertiary layer is the plasma sheath, which provides thermal and entropy buffering. This layer is designed to handle localized spikes in temperature and entropy, ensuring that these fluctuations don't propagate to the rest of the system. It acts as a shock absorber, maintaining the overall balance and safety of the craft. The final layer is the structural hull. Unlike traditional designs, this mechanical containment is only used as a last resort. Its main role is to provide a physical barrier if all other field-based layers fail. This approach minimizes the reliance on heavy, rigid structures, making the system lighter and more adaptable. When a failure occurs in one layer, the system doesn't collapse. Instead, it triggers controlled energy rerouting, allowing the remaining layers to compensate and maintain stability. This dynamic response is what makes the AEON-CASIMIR architecture so resilient, ensuring that no single point of failure can bring down the entire system. AEON-CASIMIR employs active failure detection systems that continuously monitor the craft's stability metrics in real time. These systems are designed to catch even the smallest deviations from normal operation, allowing for immediate intervention. By solving complex equations and analyzing data streams, the craft maintains a constant awareness of its own health and safety. One of the key tools in active failure detection is the Coherence Integrity Monitor. This system measures the coherence of the craft's fields over time, using advanced mathematical formulas to detect phase drift and other anomalies. If the coherence drops below a certain threshold, the system automatically initiates corrective actions to restore stability. Another critical detection system is the metric gradient Watchdog. This tool monitors the gradients of space-time metrics, ensuring they remain within safe limits. If the gradient exceeds the predefined safe value, the system intervenes to prevent dangerous space-time shear, which could otherwise threaten the craft's structural and operational integrity. The vacuum pressure sensor is designed to detect any divergence in the Casimir boundary before instability can develop. By measuring changes in vacuum energy with respect to volume, the system can identify early warning signs of boundary failure and take action to maintain stability. When a potential failure is detected, the preferred response is a soft abort. This involves gradually reducing the metric amplitude, damping plasma phases, and reabsorbing energy into the Casimir stacks. The goal is to maintain control and avoid any structural stress, allowing the system to recover smoothly without drastic interventions. If a soft abort isn't sufficient, the system escalates to hard containment mode. Here, the craft neutralizes curvature completely, collapses plasma into magnetic traps, and restores electromagnetic field dominance. This transition shifts the craft into an inertial-normal flight state, prioritizing the safety of both the craft and its occupants. In the rare event that all other containment strategies fail, the system can initiate last resort metric decoupling. This process disengages the space-time envelope, returning the system to a classical physics regime. By doing so, it eliminates metric stress on occupants and prevents catastrophic causal violations, ensuring that safety is always the top priority. Protecting the occupants and payload is a core principle of the AEON-CASIMIR architecture. The system is designed to maintain inertial isolation, ensuring that those inside remain in a locally flat space-time, even during high external curvature events. This approach minimizes the risk of injury or damage, regardless of what's happening outside the craft. Inertial isolation means that the craft's occupants experience a stable, flat, space-time environment described by the equation $ds 2 approx c 2 dt 2 plus dx 2 plus dy 2 plus dz $2. This remains true even when the external environment is subject to intense curvature or other disturbances. By maintaining this local flatness, the system ensures comfort and safety for everyone on board. Another key safety feature is the temporal consistency lock. This mechanism prevents the craft's internal clocks from desynchronizing beyond a microsecond scale, even during intense external events. By maintaining precise timekeeping, the system ensures that all onboard processes remain coordinated and reliable. The AEON-CASIMIR system is not designed to avoid failure at all costs. Instead, it's engineered so that failure never becomes catastrophic. Every instability is detected early, bounded physically, dissipated safely, and made reversible by design. This philosophy ensures that the system can adapt and recover from any challenge it faces. A cornerstone of the AEON-CASIMIR safety architecture is the early detection of instability. By continuously monitoring key parameters and analyzing trends, the system can spot potential problems long before they become serious. This proactive approach is essential for maintaining safety in such a complex and dynamic environment. When an instability is detected, the system acts quickly to physically bound it. This means containing the issue within a specific domain or layer. preventing it from spreading and affecting other parts of the system. By isolating problems, the architecture ensures that even serious instabilities can be managed safely. Once an instability is bounded, the next step is to safely dissipate the excess energy. This is achieved through controlled rerouting and absorption mechanisms, ensuring that no single part of the system is overloaded. By managing energy flow, the system prevents secondary failures and maintains overall stability. A unique aspect of the AEON-CASIMIR system is its focus on reversibility. Every safety mechanism is designed so that, once the instability is resolved, the system can return to normal operation without lasting damage. This ensures long-term reliability and reduces the need for costly repairs or replacement. Safety in the AEON-CASIMIR system isn't a one-time check, it's a continuous process. The architecture is always active, always monitoring, and always ready to respond. This ongoing vigilance is what allows the system to operate safely in even the most challenging environments. One of the main goals of the safety architecture is to maintain predictability, even under extreme stress. By understanding and controlling the system's responses to various failure modes, the AEON-CASIMIR design ensures that outcomes remain within safe and expected boundaries, no matter what challenges arise. Even when failures do occur, the AEON-CASIMIR system is designed to recover quickly and efficiently. By leveraging its layered safety architecture and advanced detection systems, the craft can return to normal operation with minimal disruption. This focus on recoverability is what sets the system apart from traditional aerospace designs. Unlike conventional aerospace safety models that focus on mechanical failure, AEON-CASIMIR's approach is holistic and field-centric. By addressing failures at the level of fields and metrics, the system can handle a wider range of threats and adapt more flexibly to changing conditions. In practice, field-centric safety means that the system is always aware of the state of its electromagnetic, plasma, and metric fields. By monitoring these domains directly, the craft can respond to subtle changes that might go unnoticed in a purely mechanical system. This leads to faster, more effective interventions. The multi-layered approach to physical safety ensures that no single failure can compromise the entire system. Each layer is designed to handle specific types of threats, and together they form a robust defense against even the most complex challenges. Redundancy is a key principle in the AEON-CASIMIR safety architecture. By providing multiple, overlapping layers of protection, the system can absorb and recover from failures without losing overall functionality. This resilience is what makes the craft so reliable, even in the face of unexpected events. When a failure is detected, the system can reroute energy in a controlled manner to prevent overloads and maintain stability. This dynamic response is possible because of the system's deep integration of field-based safety mechanisms, which can adapt to changing conditions in real time. Automatic downscaling is a key feature of the active failure detection system. When a threshold is breached, the system automatically reduces curvature strength and other critical parameters, preventing the situation from escalating. This quick, automated response is essential for maintaining safety in high-stress scenarios. By monitoring metric gradients and enforcing safe limits, the system prevents dangerous spacetime shear from developing. This is crucial for protecting both the craft and its occupants, as excessive shear could lead to structural damage or even loss of control. The vacuum pressure sensor and other detection systems are designed to catch signs of instability before they fully develop. By acting early, the system can prevent minor issues from turning into major failures, ensuring continuous safe operation. In hard containment mode, the craft transitions to an inertial-normal flight state. This means that, even if advanced propulsion is compromised, the craft can still operate safely using conventional physics, ensuring the safety of everyone on board. Last resort metric decoupling is specifically designed to prevent catastrophic causal violations. By disengaging the spacetime envelope, the system ensures that even the most severe failures cannot lead to outcomes that would endanger the craft or its occupants. To sum up, the AEON-CASIMIR safety architecture is a multi-layered, field-centric system designed to detect, contain, and recover from failures at every level. Its proactive, adaptive approach ensures that the system remains survivable, predictable, and recoverable, no matter what challenges it faces. As technology evolves, so too will the safety systems that protect advanced propulsion craft like AEON-CASIMIR. By building on the principles of redundancy, early detection, and adaptive response, future designs will continue to push the boundaries of what's possible, ensuring that safety remains at the forefront of innovation.